Hello, everyone. Thanks for joining us today. My name is Charles Rice. I'm the host for today's webinar, Simcenter Novice Non-Destructive Testing. Your presenter for today is Michael Weiner. Why don't we let him introduce himself?
Hello, my name is Michael Weidner. I work for Siemens Industry Software, and we are glad to be able to introduce our solutions for quality assurance in production to you.
Great. Thanks. Appreciate it. Well, with that, why don't we pass it to Michael and get started?
Okay, thank you, Charles, for this introduction. Well, today it's about industrial component testing with our non-destructive testing solution. And well, I will quickly go through the whole of our portfolio. And maybe you already joined another webinar from this series. In the last one, my colleague introduced the Simcenter Novice end-of-line testing. It's the testing of rotating machinery, like engines, transmissions, DC motors, and all the small assemblies like windscreen wipers and seat adjustment motors and what you can imagine. So there it's not only about go and no-go decision, but also about fault diagnosis, because at least the expensive of these assemblies have to be repaired and not thrown away. Today it's about non-destructive testing of components, and well, these components normally don't give us any signal we can assess, so we have to get some sound or vibration out of them. I will tell you how we do this later. The method is applied to, well, all kinds of single components. Some examples are given here. The third product is Simcenter Process Monitoring. The Novice Process Monitoring is a little bit a mixture of both. So you have a machine working and giving typical sound and vibration, and you have the component. In this example, it's a high voltage insulator with a metal cap crimped upon a glass fiber rod inside. And you can detect breakage either of the glass fiber rod and have to sort out the faulty component, or you will notice if something with the tool is wrong and you can trigger emergency stop and avoid further damage. So now to the non-destructive testing of components. Well, what are the fields of applications? Some examples you already could read. It's mainly sintered components like powder metallurgical parts or metal injection molded parts. There we mainly look for cracks. The testing of car body parts in the press shop. Well, there it is about cracks, but also for thinning of the material, so-called constrictions. We can also find because, well, there's a lot of tension on the metal sheet before it really cracks. And this tension, well, you can imagine it's like a guitar string tuned up, and this is what we detect. Then, of course, cast forged parts, ceramic parts, they all can be tested by this method. And what are the things required? Well, you need to get some response from the part. So you must be able to excite sound or vibration on it. Well, some geometries are not very suited for this, like a massive ball will not give you a rich spectrum. There's mainly only the breathing mode. But here you have various geometries and you get a rich spectrum and you have a way to get it excited without damaging it. And that's it. What could such a solution look like? Well, there are four basic parts. It's the hardware. You see a signal recording device and such a 19-inch device. I will talk a little bit longer about it later. And as I already mentioned, you need something to get a signal, maybe a little hammer, like this electromechanical device on the left side. And in the lower right corner, it's a slide like I use at the lab to get small parts and lightweight parts excited. We just drop them on a hard metal plate. Sometimes system comprises PC and interface cards, but often these are supplied by the IT of our customer. Then we have software with a funny name, Crackmaster. 25 years ago, nobody, at least in Germany, was thinking about drugs when calling it Crackmaster. But well, we mainly look for cracks and that it's was about what it's about. But then we need, of course, a sensor to get some signal. In most cases, these are microphones, broadband microphones preferably. In some cases, we use accelerometers. You could also use laser vibrometers, but these kind of sensors are quite expensive. And last but not least, one very important part of our system is the deployment service. And it starts with technical consulting. You call us, you write us an email, you tell us about your product, how it is produced, what are the issues to be found. And if it sounds reasonable, you may send us some samples and we will perform a preliminary study. And this is free of charge. So at this time, you don't need a budget to get a proof of concept. And we also see what are the special things about your special product. And then we can prove that it works well and see what are the requirements and quote a system. If you order it, we deliver it, commissioning, training on site. And of course, you get after sales support. If you have a question or an issue, just contact us via email or via telephone. This is the total solution. And here is the table of content. So these are the questions I would like to answer in this webinar. So how does it work? What can it be used for? What are some preconditions about the hardware and software? Some additional features, if there are special solutions, and well, when you get hungry and maybe tired, then I will present some application examples. So let's start. How does acoustic resonance testing work? Well, the basic principle is quite simple. It evaluates the state of a component based on its resonance frequencies. They are physical properties of a component. They are determined only by its internal characteristics. And which characteristics? Well, I will explain. And parts that behave significantly other than the rest are sorted out. Sounds quite simple. Too simple. Well, in serious production, the parts, they don't really sound exactly the same. They sound very similar. There's a certain scatter, but not too much. And if a part sounds significantly other than the rest, there is something with it. And what could this be? Well, a part has a certain geometry, density, mass, stiffness, elastic modulus, and all these physical properties have an influence on the resonance frequencies. So if you change any of these, we will see the change, and defects are likely to change this. And then we get the frequency of these resonance frequencies, their level, their amplitude, and if necessary or useful, the damping, the time behavior, the attenuation. And from these numbers, we get an assessment, if it's an okay part or if it should be sorted out. A little bit more into detail in practice. This method is a non-identifying method. Well, sounds bad. Well, it cannot tell you which kind of defect it is. Some of our users, they can, but it's from their practical experience. They know the defect pattern or how it shows up in the spectrum, and then they know, it's again the typical defect with which we fight against. Then it's non-locating. You say, well, I want to know where it is. Well, usually if you know where it is, you cannot detect it anywhere. And this is the advantage. It offers a full part assessment. So you can detect issues which are buried inside the part or which are not visible, non-surface open defects, things like that. And it's quite fast. Well, it works with adaptation to the current production lot. I will stress this several times and what this means and what are the consequences from this. One consequence is we don't work with the best part ever produced, the master part, which is almost totally in tolerance or without any tolerance. It's not the item with which we compare. And much more important, we don't need process representative fault parts. Well, what should this be? Examples of all kinds of faults or defects that can occur or that have occurred. Nobody could provide this, especially not if a part is only produced in future. And if a production line is set up together with non-destructive testing system. And some special thing is about it that we have an universal test setup per part type. And usually the system only tests one part type. Well, in the meantime, we already have several installations where several part types tested with one system, but it's not the normal case. And this test setup, it is defined by us in the preliminary study as well as during commissioning. And the customer later could do some small optimization of this, but normally this is delivered during commissioning. Well, what could be the benefit from it? Well, as I mentioned, it's a fast method. How fast? I will tell you. It's reliable, you can automate it, and it's able to find even unexpected faults, things that did not happen before, because, well, these parts will behave other than the rest. And okay, it's non-identifying, non-locating, but at the same time, you are able to find faults that never occurred before. Now to the next chapter. What can ART, acoustic resonance testing, be used for? Of course, our customers, they want to have process reliability, fault detection without pseudo rejects. It's the main goal. And as I mentioned, detection of yet unknown faults. What else can bring us into discussion? It's the 100% testing of production and product. Well, 100% testing of a product means each and every part. And to achieve this, you need a short cycle time for the testing. Ours is about 1 to 1.5 seconds. That's enough for getting a signal from the part, meaning some sound or vibration excitation. Then recording time signal of, let's say, 100 or 200 milliseconds, calculating the spectrum, extracting numbers, and calculating some metrics and come to an assessment. So 1 to 1.5 seconds, and then you're done. Complete automation is the normal way of implementation. Well, we also offer handworking systems like I use at the lab for my studies, but it's not the normal case. Some of our bigger customers who have several of our systems in the factory, well, they also equip their lab with a handworking station. Okay, but if you start implementing this technique, well, normally the first system is an automated one. But okay, both can be offered. Sometimes it's about documentation of the production. If it's about safety relevant parts, for example, they often are numbered or marked by a QR code or something like that. And you need a clear assignment of the test between test data and the component. And the statistics delivered by the method help you to improve your production process. Maybe you have to have a second look on the parts sorted out just to find out which are the main root causes of a defect. And this could lead to decreased scrap rate on the long term, and this could pay off. So what are the preconditions of acoustic resonance testing? We have to get some signal. And here I have an example, a pulley used for steering assembly. Well, what you see is a part settlement. What is this? A part settlement is where I place the part in a reproducible manner, because I want to have the same signal each time I repeat the measurement. So I have to put it there reproducibly and isolate it from the environment. This means I don't want to get the sound of the metal plate below. Therefore, I need these green rubber cords, and I only use 3 of them. It's the least number. What else do I need to get some sound out of it? Well, I place it reproducibly, vibrationally isolated, and I hit it with the impact device. If it was a very small component, lightweight component, I would use the slide device and let it drop on hot metal plate. And then I have some sound, I need to record it. Here, broadband microphone is used. And this leads to some time signal, and we do frequency spectrum calculation. And then we have such a result, and here's just a little section of a frequency spectrum. The part can only vibrate in some modes, in some patterns, and with each of these modes, you get a resonance frequency in the spectrum. And what to do with these frequencies. You see such boxes, and you might think, well, if all of these boxes contain a resonance frequency, it's a good part. Well, there are solutions on the market which work like this, but they are able to find out if a ring-shaped sample is broken. But usually they jump too short. And today, mainly in the automotive industry, you need to find even smaller defects. And this cannot be achieved by such evaluation boxes. So we use these only to get numbers from the spectrum. And the parameters I already mentioned, it's the maximum position of the frequency, its level, meaning the amplitude, and the damping, if it's worth doing this. From these numbers, we derive some metrics, and we even combine these metrics. Why are they combined? Well, the resonance frequencies of a part, they are not completely independent of each other. They are like a fingerprint. And now the case may occur that two of them only shift a little bit, but in the opposite direction. And this may enable you to see that something is wrong, because normally they shift in the same direction. And the combination of metrics, meaning difference or ratio, may enable you to even sort out smaller defects. At the end, you need an assessment, okay or not okay. But now you see in this graph a category like marginal, still okay. What's that? Well, missing features are these parts, let's say totally cracked, or even something of the geometry is missing. Conspicuous, they behave other than the rest, but marginal. It's due to a wish of a customer that we implemented it. Well, you can skip it, but many of our customers keep it, because if you have a production line and you see that more and more parts go into the marginal range, you see that some of your production parameters are drifting. Some wear of a tool, some furnace temperature, some pressure or anything, then you can react. You're able to react even before the scrap rate starts to increase. That's the reason why they have it. The next topic is the testing sequence with respect to the production sequence. We could have the situation that we get mixed production lots, so parts from different batches of raw material may be produced on different tools, and all of them in a box mixed up. There we can only apply testing with globally fixed limits. What does this mean? Let's have a look at one of these metrics. Let's say the feature value is the maximum position of one of the resonance frequencies. And you see the data points for many parts. And in this example, the parts come from two production lots. They are mixed and they are not labeled. In reality, all these data points are black. You cannot distinguish between the two production lots, and then you can only apply some tolerance limits and the outliers get sorted out. This is suitable for detection of large deviations. Better testing sequence is to test single production lots from the same batch of raw material or produced with the same tool. It depends on the product what is defined as a production lot. For cast product, maybe what is produced from one amount of melt. And for the powder metallurgy, it's usually the feedstock, the powder. So one bag of around 1 ton metal powder delivers very comparable results. And what happens? What is the improvement? Well, we just get rid of the second production lot. Also, the lower outlier can be sorted out because he cannot hide anymore within the other production lot, which behaved a little bit other than the blue. Okay, this increases the sensitivity for defects. The best environment of our testing is first in, first out order. This is given in car body part testing. It's at the end of the press line. So we get the parts exactly in the order in which they are produced. And how does it look there? Well, I can tell you these are the same points as in the other graphs, but they are in another order, and it shows something about scatter. The overall scatter in these other cases is combination of the process scatter and some process drift. And by drift, well, some of the production parameters may drift. Let's say production starts at 6 a.m., 19 degrees in the factory, and at noon they have 24. You might think, well, that doesn't cause a difference, does it? It does. And this is what we see here. And if we have them in, first out order, you can at 8 o'clock sort out the outlier above, and at 11 o'clock, the outlier below. And they are conspicuous with respect to their production environment. This is what counts. So there you have the best defect detection. Well, the normal case is graph in the middle. You might ask how a Simcenter Novus NDT system is implemented. Well, the first step is a very important one. You contact us, you tell us about your product and the task, and if it sounds reasonable, send us some items. We will perform a free feasibility study. It will show the applicability of the method and its sensitivity to what is defined as defect, because, well, this is arbitrary. The end customer sometimes defines something as defect which has no impact at all on the resonance behavior. So then it will show up that acoustic resonance testing is not the right method. Well, it's good to have this result in advance. But of course, we want to proceed. And some customers like to proceed with an intermediate step. They say, well, fine that it works at your lab. I want to make it work in my factory. And with all the environmental, the noise around, then they have to order some, let's say, a visit from our application engineer on site. And we will bring a hand workstation and make it work there, and maybe not only test, let's say, 50 or 100 parts like in the feasibility study, but a lot more of parts. And maybe they even ask for a rental system for a month or even longer, so that they can collect their own experience with the system. Sometimes this is necessary to get a budget or to get a new kind of NDT method on the start. Then step 3, if you have the measurements at the lab or maybe at the factory, it must be easy to define the right system components that you need for production. And usually we get into an existing production environment. The customers know how to handle their products. So how automation must look like. Some use grippers, some robots, some only need a conveyor belt and some of these tumblers, these vibration feeders. Often we get confronted with special requirements for data management, and our software can deal with this. If it's ordered, then it will get delivered, and the person will go on site to perform commissioning and training of the persons who deal with it. And of course, you will get the support later on. Which hardware and software is used for acoustic resonance testing? Of course, you need some hardware. The signal recording device I already mentioned. It provides a high sample rate of 192 kilohertz so that we can record microphone signal up to 75 kilohertz far into the ultrasonic range. And it also contains the impact control module for the sound excitation. And as I already mentioned, there are 2 ways of getting the sound or vibration of the component. And of course, we need sensors I already introduced. We need a PC with evaluation software. And what does this software do? Well, it controls sound excitation and it allows the system configuration. System evaluation will happen there. And of course, it provides some viewer for the results, and it's not necessary that it looks so complicated as in the example below, but there they were advanced users and they could interpret what they see. And you can configure the data storage, what shall be kept and what shall be thrown away. Of course, all the automation tasks can be set there. Additionally, an offline operation mode is offered, so you can review already recorded data in the office without any hardware and sensor connected to the system, just on your computer. This could be useful for optimization of the test setup. Well, of course, we talk about normally automated systems. You need some communication protocol, and there are some available. And if you have a preferred way of communication between the PLC and the testing system, well, I hope one of these solutions will cover it. Some more words about the sound excitation concepts. Of course, we use contacting sound excitation. We don't want to throw cotton balls or something. So the cracks shall work, the flanks shall clatter or rub, and this causes the difference in the spectrum. And we don't have time to do some sine sweep over a large bandwidth. So it happens in a very short time. It's pulse shape. We just hit it. It's a very short hit, and it's only one hit. And this causes the optimum excitation of all frequencies. Nevertheless, there are different concepts. The impact device for the heavier parts, it has the advantage that you can hit it several times. We have parts where this is necessary to get all resonance frequencies. So to hit a rotational symmetric part under different angles to get all the frequencies excited, sometimes this is necessary. It can also help you to avoid false rejects, because if let's say the gripper places the part in a tilted way on the part settlement or in the part settlement, well, the part settlement is narrow for the sake of reproducibility. At the same time, it shall not clamp the part because this hinders it from vibrating. But if you hit it and it was tilted, you don't hit it properly, and it's somehow a little bit clamped and it will sound weird, and you could sort it out. But well, often it settles, it drops down, and it's now properly positioned. And to hit it another time gives you the chance to see that this part is okay. A broken bell would never sound right. So if it sounds right at the second try, just let it through, let it pass. The excitation with the slide device, it also has its advantages. It enables higher throughput because you don't have to place a part into the part settlement and put it out again. You will see it in the movies later. The parameters of sound excitation. What is important to know about the part settlement? Its geometry, of course, the point of excitation, where to hit the part, and which type of sensor to use. For example, for the car body part testing in the press line, a microphone would not be a good idea. We use a vibration sensor, structure-borne noise sensor. We will see this. The slide device, this one is not for production, it's my lab toy. It offers so many degrees of freedom, it would be over-engineered for production purposes. But it enables me to test all kinds of small items with this. I have to define the orientation of the part on the test. Of course, it shall drop following its center of mass. Otherwise, it will tumble and not hit reproducibly on the hard metal plate. And I have to define the right impact angle, drop height, and this is the purpose of this feasibility study, to know how to do it and what we have to take care of. The sensors, we already had these microphones, an ICP or IEPE microphone. Well, it's an industrial measurement microphone, bandwidth either 20 kilohertz or 75 kilohertz. And you can use the directional characteristic in order to suppress disturbing noise, just point away from this source of noise. Many of our customers, they ask, well, we have a lot of noise in our production environment. Well, This may only seem so because noise comes from a point source and it propagates in a spherical shape, and the surface of a sphere increases with radius square. This means the sound gets smeared on a quickly increasing surface. What is the result of this? Okay, let's take two sources of sound. Our component under test plus some disturbing noise from, let's say, 5 meters apart. The microphone is only 10 centimeters apart. Okay, the sound of the disturbing noise is 50 times far away. So 50 square, well, only 1/2500th part of the signal will be from the disturbing noise if they have the same volume at their point of source. So you can neglect it. So distance helps us a lot, and direction may help also. And now the structure-borne noise sensor, well, it has a spring tip, so it can be adapted automatically. This is, well, absolute requirement for automated system. You cannot have a magnetic sensor or something. Well, it has a quite high bandwidth, and what is very important for the press shop, it's oil-proof, other than the microphone. Additional features, let's go through it. The adaptation, I already mentioned, it's based upon good parts from current series production. The benefit, okay, I told it. It's avoiding unpractical, unrealizable demand for process representative OK and OK samples. Give me an example for every fault that can occur and has ever occurred and will ever occur. No, not like this. And this adaptation is possible if mainly OK parts are produced. What does this mean? Well, if you have 50% scrap, then we will not know which are the good parts and which are the bad ones. Okay, we will know because the bad parts usually show a higher scatter, because somehow bad has more variations as everything's all right. But the real task is to exclude that the majority or even some of the adaptation parts contain a serious fault. And many of our customers, they cross-check their adaptation parts at the beginning of the production lot. They look at it under the microscope. Others, they have a clear load which has to be bared by the part. So they break some of them and then afterwards test tens of thousands. With others, some special methods are applied. So high resolution X-ray. You cannot perform this for thousands of parts, but for some critical parts, it is done by our customers at the beginning of the testing of the current production lot. So the first parts are cross-checked. And some remarks concerning the automated drift adaptation. We call it chameleon method because, well, it can adapt to the background just like the chameleon can adapt its color to the background. And what does it do? Well, with this automated adaptation to the process trend within the production lot, the criterion is not OK parts are conspicuous within their process environment. And, well, seems a little bit sophisticated. Well, it's the most powerful way to sort out faulty parts. It's the most sensitive way to do this. The advantage is to have always narrow limits for detection of small deviations. And if you want to learn from the sorted out parts in order to avoid such faulty parts in the future, well, some examination of the conspicuous parts be worth doing it. If you say, well, we have such a low scrap rate, we won't invest in additional examinations because our process is very mature. Okay, your decision. So are there special solutions available? This may be interesting for you because, well, you might think about the normal solution. It's the single line testing. You have one system for testing one part type or even several part types, but one after the other, one production lot after the other production lot. And you need a signal recording device, some excitation techniques, some software. Well, I forgot the sensor, but it doesn't matter here. It's good for low or medium output, but sometimes we face another situation, just like in the press shop. Left and right doors from the car body are produced at the same time. with the same tool. And they have double line production and they want to have double line testing, and they get it. So for synchronous double line production, 2 parts per tool, or for high production volume, you can have another configuration. The single recording device contains another impact controller or slide controller. And of course, both parts need to be hit somehow, and you need a special version of the software. But with 30% higher investment, you double the output. Now we are at the last point. It's the application examples. Maybe the most interesting because, well, everybody wants to see how it works and how it looks like. For example, crack detection in a pulley part for electric power steering. It's a safety relevant part. All of them have to be tested. Well, we get the sound by hitting the part with an impact device, and the recording is via broadband microphone. The testing is performed fully automatic. 100% of production, I already mentioned. We have plenty of time, 6 seconds cycle time per part. They need a clear pass-fail decision. Let's have a look. You see, we have to hit it more than one time to get all the resonance frequencies. And now it got marked. Well, we will see it several times. They work with the gripper. Normally, the drawer has a door. It is closed in order to keep the environmental noise outside. Well, in this case, this was necessary. Let's have a look at it again. Okay, it gets in. This is not the microphone, the slim part. It's the marker. So in this case, every part which got tested and assessed as being an okay part is marked, so that at the assembly line at the car plant, they can see this was tested and it was okay. And what else? You see a red part on the left, and well, it's not exactly like the parts on the test. It only has the outer shape, but it's from stainless steel. It's not a sintered part. What it's good for? They use it for a performance test. It doesn't show the same spectrum as the part on the test, but it shows the same spectrum today, tomorrow, in a week, in a month, in a year. And with this part, well, you just get it into the drawer, let the system hit it once, and then you get the spectrum, and you test the impact device, you test the microphone, all the cables, if the part settlement is still okay, all at a time. And well, it's a very good way to have a first test that all the equipment works well before you start another production lot or new shift or a new week or something. Okay, there are plenty of companies using Simcenter Novis NTT for testing sintered metal parts, like GKN Sinter Metals. It's the biggest player in this field, an American company, or Schunk Sinter Metalltechnik, or Bosch in several countries, or in Italy, Carposint, or in Denmark, Syntex. Okay, let's go on to the next example. It's car body part testing in the press line. There, again, we hit the part with the impact device. Well, it can be configured. The impact device, well, different voltages can be applied to the acceleration magnet. And for testing car body parts, well, we hit them not so tenderly, but we want to get a proper signal out of them, and you won't see anything at the surface. And the sound recording, as I mentioned, is achieved via a vibration sensor. Also, this testing is performed fully automatic. Each and every part is taken out of the last station of the press line with a gripper and put onto this part settlement with some rubber cones. And then it's hit, it is assessed, and if it's okay, the other gripper just puts it on the conveyor belt. This all is within the safety fence. And if it's a not okay part with thinning of the metal sheet or a crack, it will get turned by, let's say, 60 degrees, and the workers at the conveyor belt will easily see, okay, there's something wrong with it. Well, several companies use Simcenter Novus NDT for testing of car body parts, for example, Ford in Saarlouis in Germany. Unfortunately, I don't have a movie here, but here I have one. For cast and forged parts, they are also tested with this system, for example, at Hirschvogel Automotive Group or Job Automotive. And how this could look like can be seen here. I just used this video to show how a slide works. Well, you see the parts, they get aligned so that they have the same orientation. They arrive at a release pin, then go down the guide rail, hit the anvil, and there's the microphone hidden behind. And well, you hear there's a lot of noise in there, but they have some acoustic foam around. And okay, they have the assessment result, and then you see a time signal containing all the frequencies, and then you see the spectrum that is calculated thereof. And here's another representation of the spectra of 45 parts, and here's a list of the results. 2 parts are faulty. Okay, that was it. So you see the cycle time was quite high, about 2.7 seconds per part. There's a conveyor belt for the good quality items, and you can believe me, there's another conveyor belt for the bad parts and for the adaptation parts, which are cross-checked. Okay, so thank you for your attention. And well, me and my colleagues would be glad if you propose some parts for being tested by Simcenter Novus NDT. Thank you.
Thank you, Michael. Great presentation. Very interesting. And please don't hesitate, as you said, to reach out to us for more information about your application and how we can help. And other than that, have a great day and hope to see you at another webinar in the future.